We're going to look at significant figures in this video, so we're going to be recapping the last two little intro kind of activities that we have done and kind of writing all of them down in an actual set of notes. So, first thing are significant figures, and what are significant figures? And you're going to look at what number you're guessing when you're dealing with significant figures. Okay, a significant figure is the number of digits, okay, that are known for certain plus one or uncertain digit that you are guessing. Okay, you should always be guessing one place past where you have an actual line for something. Okay, so always guess one more place. So the question kind of becomes, if you're looking at a number, and I say it's 1200 versus a number that's 1200.00, all right? Now think about what number you're actually guessing in this particular part, okay? Here, I'm guessing a 2 because I'm saying, well, it's about 1200, okay? So it's like I'm saying, well, it's about 1,200 acres, all right? You wouldn't say, well, just by looking at a piece of farmland, I have 1,246.35 acres, okay? Just by a pure guess when somebody's looking at it, okay? But say if I'm measuring something on a balance, I might say, okay, I have exactly 1,200.00 grams. That would be a good guess. That would be a very precise one. The balance itself is guessing that last zero. Okay, so if we look at these meter sticks, okay, that we have over here, it's basically what you did in your little intro part. You say, okay, I'm measuring the same thing. I just have different meter sticks that you're using, okay, a different precision, all right? If I have this one, I'm going to say it's 0.6 because, well, it's somewhere between 0 and 1. So I know it's about halfway there, okay? And the second one we're saying, well, okay, I have 10, 20, 30, 40, 50, 60, it's about 61 centimeters. They said it in meters instead of centimeters. Here I'd say, well, maybe that's about 60 centimeters. You know what? I know it's at least 60. Well, you know what? It's at least 61 centimeters. In the bottom one, you say, well, it's 0.607 meters, or you know what? I know exactly where 60 is. I know it's exactly, there's 61, and you know what? I think it's a little bit under that. So 60.7 centimeters or 0.607 meters, same thing. So the more precise your piece of equipment gets, the more precise your number needs to be, all right? It needs to reflect it. So we're going to start off by looking at how do you read lab equipment, all right? So if I look at a burette, for example, okay? Burettes are like upside down graduated cylinders. Okay, they read backward because it's talking about how much it dispenses. So the top of a burette, okay, it's going to say 0, and the bottom ones for what I have are 50, okay, and they're milliliters. So you start with it all the way full, and you let some out of the bottom, and then I read it and say, okay, well, that's how much I actually dispensed into my beaker, into my container. Well, if we look at these, and I have another example as well, okay, you see, okay, well, there's 3, here's 4 at the bottom, and I say, all right, there's 3.1, 3.2, 3.3, there's my meniscus. So I know it's exactly 3.3, and you know what? I think it's right on. So I would say 3.3 milliliters. If somebody else looked at that, they might say, well, you know what? I think it's 3.2, but it's real not quite 3, so 2.9. All right, or 3.1. But you still have the same number of significant figures. The same thing would go for this burette, okay? I have 3, and I count down 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, and this picture is saying that it's 3.90. I might call that, you know what, I think it's a little above it. I'm going to go 3.88 milliliters. But notice how it's kind of upside down graduated cylinder. You don't have 0 at the bottom, you have 0 at the top. Okay, these are very, very precise. Because you should have 2 decimal places you're reading with here. I have one place I know, and then I'm going to guess one more. Always guessing one more. An Erlenmeyer flask. Erlenmeyer flasks are much harder to be accurate with and much harder to be even any kind of precision with, okay? Because Erlenmeyer flasks tend not to be in multiples of 10 or increments of 10. And I'm going to show you a couple of examples. You have both of these in your drawer, okay? I have a 250 milliliter and a 125 milliliter. So what we see here, my 250 milliliter, okay, I have some increments. It says 50, and then 100, then 150, then 250. And it's telling me, well, that's halfway between 150, so that's about 75. And between there, we're looking at about 125. Okay, so they're good estimators. They're not good for significant figures. Because if you say, for example, all right, I have a water line that is, and I'm going to undo this one here, that is somewhere right maybe here. Okay, so I fill this up and I've got about right there. Okay, you might think, well, you know what? I know I've got 100. I have, at least 100, not quite 125. So I'm going to say I have 122. You cannot say that. Okay, you could not call us 122 milliliters. Because do you have any idea where 120 is? No, you do not know where 120 is. So you cannot say 122. You would have to say 120 milliliters. And that's what I mean by they're not very precise. They're very good for just about, but they're not going to get you barely within 10. All right, the same thing goes for 125 Erlenmeyer flask. Okay, we look at this water line right here. Say, okay, I know I've at least got 75 and 100, so you know what? I might call that 83. And unfortunately, you really can't do that because do you have any idea where 80 is? No. So I'd probably say more, you know what? I think I've got about 80 milliliters. That's as good as you can get with an Erlenmeyer flask. Okay? They are not very accurate at all. You have to know every single tens place or ones place to be able to guess the next place. All right, let's look at graduated cylinders. Okay, so a graduated cylinder is a lot easier to read. Okay, they tend to go up by 1 milliliters. Most of them, all right, they are much more accurate because they usually have nice increments that are powers of 10. I will tell you that even though they are better than a beaker or a flask, please be careful because sometimes they'll go up by 0.2 and 0.2 is not 0.1. So if it goes up by 0.2 increments, you can't guess an extra decimal place. And we're going to look at a couple of examples. All right, so here I have two graduated cylinders. All right, the one here is a little more what we probably have in our drawer. Okay, see I have 5, 10, 15, 20. But if you look in between it, each one goes up by 1. So if I know every single one, it means I can guess a 0.1. So if I look at this right here, you know what? I would say that, well, that's 10, 11, 12. It's probably 13. And I think it's right at 13, so 13.0. If we look at the one on the left, it's a little bit larger graduated cylinder. Okay, we have 50, 100, 150, and each one is 10. So if my water line was somewhere in there or liquid line was somewhere in there, I would say, okay, well, I'm not 50, but I'm not 60, so I am maybe 58 liters. All right, it goes up by 10s. You got to guess your ones. Okay? Beakers. Beakers are not very nice either. Beakers are very unprecise when you're dealing with significant figures. They're just as unprecise or as inaccurate as a flask. Mostly because, again, the intervals are not increments of 10 or powers of 10. Okay, so let's look at a couple of examples for these beakers. And I'll show you because you have some of these in your drawer. All right, if we look at, this 100 milliliter one. Okay, I've got 20, 30, 40, 50, 60. So actually with this one here, I could say, well, I know it's not 40, not quite 50. I'm going to call that one 48 milliliters. That's pretty good for a beaker. Mostly because this one goes up by 10 minus the initial 10 one, okay? But if I look at this 250 milliliter flask, which we use a lot more, notice how the increment here is 0, then 50, and then 100, then 150, then 200. I'm kind of going up by 50s or essentially actually 25s. So it works the same way as a flask. If you have it like that, right, even though I know it's between 50 and 75, I cannot call that 63. I'd have to say, well, that's probably right about 60 milliliters, or maybe I could say, that would be about it. Maybe I'd call it 70. I could not say 63 because you have no idea where 60 is. Okay? On the next one, looking at thermometer. Should be very accurate. They should usually have a nice even graduations. They tend to be up by 1 degree. So you usually are going to read them to the 0.1. Just watch that one. Okay, but they usually are very nice increments. Just so you know, too, the difference between 1 degree Kelvin and 1 Kelvin and 1 degree Celsius are the same thing. So if I go up from 25 degrees Celsius to 26, that's the same thing as saying if I went up from, 200 Kelvin to 201, 1 degree is the same. We'll talk more about that later on, but that's the thermometer. Okay, the last thing here we're going to look at for in terms of lab equipment is a balance. Okay, and there are kind of two types of balance. The electronic balances are the easy ones. Obviously, the balance is the one guessing for you. You don't have to make any guesses for that one. Be careful, some of the balances in my room are 0.1. Some of the balances are 0.1 grams. Some of them are 0.01 grams. All right. The other type of balance, though, is a triple beam balance. Okay, and I'll show you how to read those ones. Or a quadruple beam balance, depending on which one you have. We actually have the quad beam balances. These are the ones you have to do by hand. And I'll show you a couple of examples on how you read these. Okay, so we're going to start off with reading a triple beam balance. And these ones are usually a little out of order. These are not the ones that we have. Okay, you start off with the 100 here. That's okay, I know it's at least 100. I see the little guy here is on 40, so I know it's 140. Then I go to my ones place, I know it's 140. And I see, well, you know what? It's between 144 and 145, 144. I see that the little end here is in between 144.5 and 144.6. So I'm going to go 5, 5. Because it's in between 0.5 and 0.6. Okay, so 2 decimal places are what you need for this one because you're reading one past. The quadruple beam ones are the ones that we actually have. We have this one here. All right, so the reading for this one would be 170. I have 170 and 171. And then I look here and say, okay, it's 171.4. That's 0.4. And then I keep going and I write, all right, I count, and I'm at 5, 6, 7, 8, 171.48. And you know what? To me, that looks like it's probably about 4. So that one will have 3 decimal places because you have an extra arm here. There are 4 different arms. It's telling you exactly 1 and then the 0.1. The other one told you just between 4 and 5, and then you had to guess one more. So this one is actually a quadruple beam balance. These are the ones that we have in our classroom. So actually, those are very precise instruments. They may not be as accurate as an electronic one because it's not electronic. You're dealing more with your error and is it calibrated right and everything like that. Okay, let's go on away from lab equipment now and look at rounding. Be wary of your calculator. Okay, I know it's right, but just because your calculator gives you 18 digits doesn't mean that every single digit is a digit that you want. So for example, I have my calculator right here. If I take 15 and I divide that by 24, it tells me that it's 0.625. So I have 0.625, which is 15 divided by 24. What I will tell you is I'm going to have to round that to 2 significant figures. We'll talk about that in the next part. You cannot have a very precise answer come from 2 very vague numbers. Okay, so even though your calculator tells you it's 0.625, it may not be. Okay, but if I were to round this one, remember that if it's a 5, it will round the next one up. You do 5 and up, round the next one up. So I might round this answer to actually be 0.63, and we'll talk more in the next section here about why you use 2 significant figures for this one. Okay. Another thing is if I wanted to say multiply 124 by 13, say so 124 times 13 tells me it's 1612. Well, what I want you to do is round this one to 2 significant figures. So that means I only want to have these 2 be significant. So that means this 1 does not round that 6 up. So I'm going to have 1600. Because I cannot have just 16 because 16 is way different than 1612. Just because you have 2 significant figures doesn't mean you drop every single number after 2. We'll talk. You should have looked in your significant zeros why these 2 zeros on the end actually are not significant. Remember, they're what you call placeholder zeros. Okay? Which makes sense. That's why these aren't significant. Because all we're doing is showing you how big the number actually is. Okay? So let's move on to mathematical operations. We're going to add and subtract first. Okay? How you do this, and I'll show you the example for it. You want to look at the least number of decimal places, okay, for one of the things that you're adding together, okay, is the number of places to put in your answer. So we're going by the least number of, I should be careful, decimal places. I guess I didn't write that out. The least number of decimal places is how many decimal places you should put in your answer. It's the big thing, decimal places. So if I want to add two numbers, so say I want to add 0.1201, and I want to add to that 2.3. Well, if you think back to your old, elementary, okay, if I'm going to go add these two numbers up, I'm going to have 2.4201. Well, how significant figures work is that if you have absolutely no idea what numbers go here, there's no way you can put those in your answer. So even though your calculator will tell you that it's 201, that's because it had nothing to add it to. But these are not significant. The answer here would be 2.4, because that is all you know about. You cannot add a number you have no idea what it is to a number you know and get out an answer that you know. That doesn't make any sense. Okay? For multiplication and division, here we're looking at not the least number of decimal places, but the least number of significant figures. That's how many significant figures you put in your answer. So for example, if I'm going to take 16 and multiply by 144, my calculator will tell me that it's 2,304. This one only has two significant figures. This one has three. Therefore, my answer can only have two. We don't deal with decimal places because when you multiply, you don't line up decimal places, okay, or divide. So we have to go by overall total number of significant figures for each one. So I'd have to actually round that to 2,300. So everybody every year is like, well, your number's becoming less precise. How is that possible? How is that actually right? Well, your number is not less precise because you're rounding it. This number, these digits here, are nonsense because you don't know the rest of those digits for that 16. Okay? So it may look like you're rounding up a whole bunch, and you are, but it's because one number is not very precise. Okay, so I'm going to run through real quick the counting significant figures rules. You had these already once, okay? Any number between 1 and 9 is significant. So for example, 4263, that has 4 significant figures. I always use significant figures, SF, okay? Any zero between two non-zeros is significant. It's called a captive zero. So 205, that one would have 3 significant figures. That zero in the middle counts because it's just, I know it. Okay, I know it's 200. I just know, well, 205 is my guess. Okay? Leading zeros, you have 0.00324. These ones are placeholders, they called those. Okay? There's a placeholder zero. You do not count those. You wouldn't count them if it was 125 and you had 2 zeros in the front. So don't count them on decimals. Okay? Those do not count. Trailing zeros, okay, are the other end. These two are placeholders. Okay? You have 64800. These two here are not significant. They're just telling us a really big number. But my guess was actually the value of 8. I thought, well, you know what? I know it's 64,800. Okay? Decimal numbers. The trailing zeros after a decimal, 0.96300. Those don't need to be there, which means they're there for a reason. Somebody put them there to tell you, you know what? I know exactly that it's 0.96300. It's ended up to be right on the line. Okay, those are very significant zeros. This front one again is not. It's a placeholder. It helps show that it's a decimal point. Keep in mind, hey, you walk through all of these on those two PDF files on your iPad.